Hi students, this is your very first recording for the Science Support Group. Don't forget that you are going to be asked to watch these extra videos just once a week for the next 6 weeks. And after that time, I will ask you to take my science checkpoint number 1 again, the one we took a couple weeks ago. So welcome to our first recording. The goal of this video will be to summarize the difference between Newton's first and second laws, and then we're going to kind of talk about and carry out a simple investigation which provides evidence that a change in an object's motion is dependent on the mass of the object and the sum of the forces acting on it. So let's jump in and talk about Newton's first law. Here it is. An object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. So take the example of my car here. You can imagine any toy car. If that toy car sits there, it's going to stay at rest unless acted upon by an unbalanced force. Who could be that unbalanced force? It could be you, it could be a kid, it could be a table tipping and gravity pulling that car down. But there does need to be an unbalanced force to get that car to move, okay? And what is a force? A force is any interaction that will change the motion of an object. So I could get that car to move, or I can get my phone will just sit here all day long unless I do something to change it, and I can be an unbalanced force for that phone. So in class I gave this example of the classic pulling the tablecloth out from underneath the items sitting on the table. This is a great example of Newton's first law. In other words, saying that an object at rest is going to want to stay at rest. So underneath this tablecloth, just a few moments ago, was underneath that, all of those items, right? Everything was at rest. Now the tablecloth had an unbalanced force given to it, right? The man was the unbalanced force of pulling that tablecloth out. However, the man did not pull on any of these other objects, right? Which is why Newton's first law very well describes this. The objects at rest stayed at rest, right? And the objects in motion, of course, were in motion and stayed at motion until he stopped pulling the tablecloth. But this is why this trick works, is because of Newton's first law. This is a question that was on your checkpoint. So based on what we've just talked about, what do you think the answer would be? An object stays at rest until what happens to it? All right, so hopefully you had a chance to look at that. What did you select? Let's talk about it here. Friction builds up and moves the object. Gravity overcomes friction. An outside or unbalanced force acts upon the object. Inertia releases it. So based on what we just talked about, I hope you guys feel like the correct answer here is an object is going to stay at rest until an outside or unbalanced force acts upon the object. Okay, so the correct answer there is C, or the third one. One way to kind of extend this question about Newton's first law is I want you to think about, would this task be easier with plastic plates or with heavy porcelain plates? And we may come back to this in just a moment because I think that we'll talk about this when we talk about Newton's second law, which will be right coming up next. Another question I want to stop and have you guys think about is, would this task be easier with a towel or a silky tablecloth, and why? I hope you guys agree with me that a silky tablecloth would be a lot easier to complete this because there's a lot less friction. Friction is that force that kind of that would stop this from happening so easily. So if there was a towel under there, a towel with all those little you know, little loops on it. As you pull it out, there would be a much greater force to overcome than like a silky smooth tablecloth. So there's other factors that go into it as well. Let's take a sports example here and talk about this golf ball. Okay, I don't know if you play golf. I don't really play golf, but let's talk about this ball, right? Newton's first law says that this ball is going to stay at rest, just right here, like on this, okay? So my first question for you guys is, what forces could cause this ball to move? Great. And so, yeah, you guys probably wrote some great things down. Just in case you didn't think of it, of course, you know, hitting the ball with a club, wind could cause the ball to move, kicking it, anyway, and some kind of unbalanced force could get this ball to move, right? If I can write the word unbalanced. All right, and then my second question for you guys, I want you guys to respond to, is let's say the ball is in motion. Okay, so I've just hit it and it's flying through the air. Why doesn't it stay in motion? I want you to answer that first. Why doesn't it stay in motion? Okay, great. So I think you probably put some of those thoughts on the board that I'm thinking of. Well, the biggest reason that ball doesn't stay in motion is because of that ever-present force on the earth called gravity. Okay, so the second that ball gets shot up into the air, gravity is going to be pulling that ball down. It's a force, you know, from the center of our earth that is pulling everything in. So if we were in outer space and you hit that ball literally would not ever stop. Unless, of course, it was acted upon by an unbalanced force, like maybe the ball were to run into a spaceship or an asteroid or something like that. But an object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an unbalanced force. That, my friends, is Newton's first law. Let's now jump into Newton's second law. And once again, the concept of it is not that tricky. It's just more remembering which law is which. So Newton observed another property that affects how an object's motion changes. It's the mass of the object. Okay, so let's take a look at the two shopping carts. Okay, we'll call this shopping cart A, and we'll call this shopping cart B. If you were in the grocery store, we'll assume these two shopping carts are identical. I know they look a little bit different, but let's say they're the identical shopping cart. Which shopping cart would require more force to move? All right, I hope you guys put B, right? B would definitely require more force to move it. Why is that? Well, you probably can guess, well, there's bananas in there. There's milk and there's more mass. Okay, so that is what I'm really trying to get at here. Is this, read this with me if you'd like, the relationship between the force of an object, its mass, and how its motion changes is called Newton's second law. Basically, if you can just remember Newton's second law and the shopping carts, think about two shopping carts. One is empty, one is full. Which one? There's two shopping carts for Newton's second law, and when one has more mass, it's going to require more energy to move it. All right, so I like to kind of put big ideas by themselves on slides. So if you want to read this with me, the greater the mass of the object, the greater the force needed to achieve the same change in motion. So I can give an example of me needing to go out running. Sometimes I go running, and I go running by myself, which is still hard. It was hard, but I can do it. But some days I have to take a child with me. I push them in a stroller. And you better believe that it takes greater force to achieve the same change in motion. So I'm still going to run. I'm still going to run my same route, but it's going to take more force because I have more mass. Okay, there's greater mass. It's going to take greater force. So at the beginning, or a couple slides ago, we were talking about that grand magic trick of the table, right? And I asked a question, would it be easier to pull out a tablecloth underneath a, I'm just trying to draw my best tablecloth. Would it be easier to do a plastic plate? Would it be easier to pull out a tablecloth underneath a plastic plate? Or would it be easier to do with like a big glass heavy porcelain vase? What do you think? Any thoughts on that? You can go ahead and take a guess. All right, so I'm not sure what you guessed, but it has to do with Newton's second law. Okay, tell me which of these two items here has more mass. Does the plastic have more mass or does the glass have more mass? Well, I hope you're able to agree with me that the glass definitely has more mass. So the reason why it's easier to pull out a tablecloth underneath glass is because there is more resistance to change. That glass sits on the table, it's heavy. So as I pull a tablecloth out, that heavy glass is more resistant to change because it has more mass. It's going to take more force, maybe like a towel of friction, or anyway, it's going to take a lot more force to move this glass because it's more massive. So that question I asked a few slides ago, I wanted to make sure I came back to it. So let's compare Newton's first and second laws, okay? Just so I want to make sure you kind of are able to remember the two separate laws and keep them separate. So let's remember, and you guys can review these and read them with me. First law, if at rest, this bike will stay at rest. If in motion, this bike will stay in motion, unless acted upon by what? An unbalanced force. Very good. And the second law, okay, I can think of these. I wish I could try riding this bike. I don't know if I would do a good job. But the second law says that the greater the mass of the object, the greater the force needed to achieve the same change in motion. Okay, so first law, things at rest are going to stay at rest, things in motion stay in motion unless an unbalanced force. Second law has to do with mass. So the greater the force, the greater the mass of an object, the greater the force needed to achieve the same change in motion. Here again is another question that was on our checkpoint. So I want to go over these because I know that many of you maybe missed some of these questions. Here's the question that I asked. Students at Treeville Junior High completed an experiment where they made paper airplanes. They added penny passengers to these paper airplanes to see how it affected the flight of the paper airplane. Which of Newton's laws was primarily being tested? So based on what we've just talked about, guys, I'll let you guys have a chance to answer this. Do you think it's A, the first law, B, the second law, C, the third law, or D, the law of gravitation? All right, I hope that you remember that we just talked about how Newton's second law is all about how mass is going to change the amount of force or the outcome of what is going to happen, how mass plays a role in force. Okay, so I hope you put B, the second law, because that is Newton's second law is all about mass and how mass is going to change things. So, of course, another question from that, it kind of goes along with the same question before, but it says here, students at Treeville Junior High complete an experiment where they made paper airplanes. They added penny passengers. They used pennies as little passengers to these airplanes to see how it affected the flight of the paper airplane. The students threw the paper airplanes with the same amount of force each time. Okay, so they used the same amount of force. The table below shows the data collected from the experiment. Ooh. After analyzing this data, what could the student conclude? So let's, this is a question I want you guys to take a look at and try to answer now, and maybe if we talk through it, you'll be able to select the right question. But let's say we have, like, so here's the number of pennies, right? These are the penny passengers I'm going to add to my paper airplane. So first, I'm not going to have any passengers. I'm just going to throw the paper airplane, and the average distance it goes is 5.5 meters, okay, without any passengers. Then I add 1 penny to the airplane, and I continue to throw it with the same amount of force each time, but the paper airplane doesn't go quite as far. It's only 4.9 meters, right? So you can see that the data has a trend that as I add more penny passengers, what's happening over here? Are those numbers going up or down? I hope you're able to see that those numbers are decreasing, right? The numbers are decreasing, and that's that's what this question is basically asking. And as we take a look at these options now, what would the student conclude based on this data? Would it be A, as the number of pennies increases, the average distance the paper airplane flies increases? Would it be B, as the number of pennies increases, the average distance of the paper airplane flies stays the same? C, as the number of pennies increases, the average distance the paper airplane flies decreases? Or would it be D, there's no relationship between number of pennies and average distance of the paper airplane? All right, I hope after that you picked letter C, because that's the correct answer. As the number of pennies increases, right, as we put more penny passengers into that paper airplane, we see that the distance that the paper airplane flies decreases, okay? So as you see these questions, a lot of times they're not all that tricky. It just takes a moment to kind of take it slow, take a look at the data. There'll always be lots of questions where you have to look at data and kind of check out what is the trend. Like as one gets bigger, what does the other one do, okay? So hopefully you got that one right today. All right, so I just wanted to take one quick moment before we finish up here today. And this is not a bike and weight graph. Let's say I wanted to take the data from the penny passengers and I wanted to graph it, okay? Because I want you guys to feel comfortable graphing things. So if we had to take the penny passengers, I'll just shorten it there. What I would put on the x-axis down here would be the number of pennies, right? So here would be 1, 2, 3, 4, and 5 pennies. Okay, we'll do that. And I'm not totally sure on, and here's 0. And so this would be the number, we want to label the axes. This is number of pennies down here. Okay, this is not going to be great. And then on the y-axis, we would want to do, this would be the distance. This is really going to be tricky. Riding sideways. So this is the distance. I'll stop there. In meters. I'll put a little m here. And we'll also count it off to 5. 1, 2, 3, 4, 5, 6. I'm not entirely sure on the data from my previous slide, but I can't really go back while I'm recording. So I'm just going to kind of estimate. I know that when, let me get a different color here. When we were at a number 0 pennies, when there were 0 penny passengers, the average distance was a 5.5. When there was a 1 passenger, the average distance was a 4.9. When there were 2, we'll say it was right in here. 3 was a 3.3, and I'm just kind of making this up, but I want you to see that we can graph the data and then we can draw a line of best fit. Not great, but we can kind of see the relationship, and we see that that as the number of pennies increases, the distance decreases. And that's why that slope of the line is negative. It's coming down because as the number of pennies increases, the distance is going down. So we can take the data that we collect and we can graph it. And that will be something I want us to get really comfortable doing this year. All right, guys, thank you for watching. That's it for this week's recording. Thank you for participating. Watch for next week's recording as well. And I will see you guys next week. Thanks for watching.